Welcome to Partial Differential Equations, Lecture 20. We'll be continuing at looking at Green's functions for the wave equation in 1 and 2 dimensional cases. So just to sketch the geometry of something we're looking at, we're trying to solve the wave equation on a domain of n dimensions. Here's the 2-dimensional case that's presented here. The initial condition is specified at time t0. You have a boundary that does not change in time for the examples we're looking at. You have a field point where you want to know the solution, and you have a source point Q that then you use to integrate over the whole domain given the data given to try and get an explicit form for that solution. So here the equations. We want to solve the D'Alembert operator is equals to a source. We've defined this D'Alembert operator to be box, which is basically Laplacian squared minus the second derivative of time with respect to time over c squared. And this is our operator in Rn. We let R be the difference between our field and source points. So in other words, R connects these 2 points in the spatial domain. So it goes from R to R. We let T be the difference between our source and field points in the time domain. And we define R in the general n dimensions to be any vector with components x1 to xn expressed in terms of the unit vectors I1 and 2in. Okay, and given these things, the way we're going to construct our solution that we integrate over is simply we apply the same operator to a Green's function, but to the source points, and we set that equals to the delta function of the difference between the spatial components of the source and field points and a delta multiplying the delta function as the difference between the time components. And we have the additional condition that the solution is causal, in other words, that the Green's function for the source point, if the source point's time is greater than the field's point time, it must be 0. In other words, only the Green's function is only non-zero in the region over here. Okay, and then we showed that we found the general solution for a finite as well as an infinite domain, and we went on further to show that for an infinite domain, it's becomes somewhat simpler. We basically have that the boundary goes to infinity, so the boundary terms are lost. We have that our function u of r and t can then be constructed by this integral over the source term g multiplied by the Green's function plus the initial condition specified at time t prime is equals to 0 times g derivative with respect to t prime minus g times ut, which is the initial velocity or initial momentum given to the solution on this initial condition. And then we went on and we proved that the symmetrical solution to this Green's equation basically can be found in the infinite domain by considering just the difference between the source and field, considering a function where you just have the difference between the source and field point because there's no other symmetry in the problem, and the difference between the source and field time. And then we derived using a Fourier transform that you could generally express this function as this integral, where we explicitly construct the integral with respect to time already, and now all that remains is that you have to evaluate this integral with respect to space for your various dimensions. It's dimensionally dependent, as we discussed in the last lecture, and as we will see in this lecture. Just one comment. In the last lecture, I made a sign mistake when I did the complex integration. I forgot that the direction in which you transverse the contour when you apply the residue theorem has to be such that the interior of your domain is on your left-hand side. So it has to be positively orientated contour. And I gave you a negatively orientated contour in the notes. So I made a minus sign mistake. So I fixed the notes and will upload the new notes. So please go and have a look at that. Anyway, so this actually differs from what I had the last lecture with a minus sign. Okay, and as I mentioned, it's dependent on the dimension of n. And in 1D, we found up to a minus sign that if our R is just a one-dimensional difference between your source and field points in the spatial context, and we showed that our Green's function is equals to C over 2 h of R plus Ct minus h of R minus Ct. And since minus Ct is positive and R is always positive, this thing is always equals to 1. Whereas this thing depends on how large R is. It's equals to 1 if R is greater than minus Ct and 0 otherwise. So h is the Heaviside step function, as I've sort of implied by the discussion. And what we then get is that this above Green's function n equals to 1 is non-zero if R is less than or equals to Ct minus T prime. Remember, we've restricted the Heaviside, the function to be non-zero, or the Green's function to be non-zero only if T minus T prime is positive. Okay, and we get that the value is minus C over 2. And what I want to do now is simply show you, and there's a I simply want to use this Green's function to try and derive what we derived, I think, in lecture 6 and 7, the solution we already know for the wave equation. I want to show you that the thing that we've derived abstractly for all dimensions works at least well in the one-dimensional case that we know. Okay, so another way of expressing this Green's function is simply to write it as a different Heaviside step function. We can say that G1 is equals to minus C over 2h of Ct minus T prime minus x prime minus x, in other words, R. Okay, so this expression is exactly equivalent to the one up there. I've just now using one step function. Okay, and I'm still missing the prime here, I apologize. So we're now also going to need the derivative, because the derivative goes in here when we work out the derivative with respect of g with respect to t prime. And if we do that, the derivative of step function is just a delta function multiplied by the coefficient in front of t prime. So it is minus c over 2 times c times minus, so that's c squared over 2. Okay, and what we can now do is we can substitute this into our expression for u and then conduct the integral. The one thing to note is that this integral was derived considering the fact that we are looking for a Green's function over an infinite domain, and because we have a symmetric Green's function, it can potentially, this omega t prime, or this slice omega that we integrate, the spatial slice omega that we're integrating over, basically involves the whole of the flat plane in R2. The thing that restricts this integral is the fact that the Green's function here, g, is merely the Heaviside step function. So it's this Heaviside step function that then restricts the region for a given field point that we integrate over. And in fact, for a specific field point x and t, we have that this Green's function g is only non-zero in this green triangle, where it's equals to minus c over 2. And you can see that the boundaries of the triangle are given by the lines at which this interior function is equals to 0. So if you have x prime minus x is equals to minus t minus t prime, and here you have that x prime minus x equals to plus t minus t prime. Okay, so this is the domain of dependence that we discussed in the lecture, I think, 7. Okay, if we now look at the first term, we see that this, when we integrate over this boundary, you're just integrating over now the place where the function is non-zero, so this green box, and you have the value of the Green's function, which is equals to minus c over 2 divided by c squared multiplied by g, so you have minus g of x prime t prime over 2c. And notice that when we looked at lecture, I think 7, there was a plus sign here, plus f, but it's in fact true if you look at the definition of how g is defined here, that g is in fact equals to minus f used in that derivation over there. Okay, so the first term agrees exactly with the Delambre solution that we derived earlier. Let's now look at the term where we're integrating over omega 0, 1 over c squared u of gt prime. Okay, and the derivative of the Green's function with respect to t prime was worked out here, and that's just c squared multiplied by this delta function, and over 2, so c squared times 1 over c squared is gone, so you have a half 2, and then you just have u evaluated at the points at which this function is 0, which is basically x minus ct. Notice that we're working on the initial domain, so t prime is 0. So it's x minus ct plus x plus ct. Okay, and then the final term over here, we just have the Green's function. So we're now again integrating over this domain with t prime is equals to 0. And we get, and it's minus, but there's another minus there. So it is c over 2 divided by c squared. So it's 1 over 2c, the integral from x minus ct to x plus ct of the derivative, the initial condition where you give the derivative of u with respect to t. Okay, and this is exactly the solution that we derived earlier for the wave equation using sort of more specific techniques. So now let us move on to the Green's function in 2 dimensions. It's quite interesting that while the technique is almost exactly the same, some of the properties of the solution varies, and this is true also when you go up to 3 dimensions that we'll do in the next lecture. So once again, we start with this general expression that we derived in lecture 19, and we just have to evaluate this integral now, given the fact that we're working in 2 dimensions. And the steps of doing this will be due again in 3 dimensions, but I'm just going to go through it in detail because it is kind of nice and it's useful when you work on other 2-dimensional Green's functions. So the first thing we're going to do is we're going to choose polar coordinates that is centered at the place where r is equals to 0. Okay. K is equals to 0. And we're going to, in polar coordinates, the area element is just the square root of the norm of the Jacobian, and that's equals to k d phi dk. Okay. And k is basically a radial-like coordinate in k space, and it goes from 0 to infinity because we're going to integrate over the whole 2-dimensional plane in k space. And we're going to have phi is an element of 0 to 2 pi, and without loss we're simply going to choose our axis of k because, or sort of the kx direction, so that r dot k is equals to rk cos phi, which then defines the phi coordinate. So there is some arbitrariness in how we orientate the original choice of the k or the k axis, and we simply choose it that this condition is true. Okay, r now is the distance between, is the norm of the difference between our source and field point spatial vectors. And using these things, we can now express this integral for g2 as c over 2 pi squared, integral from 0 to 2 pi. That's the angular integral, the integral from 0 to infinity over dk. And the contribution of this k in the area element very fortunately cancels out the k in the integral over here, and we're left with sine tck e to the ik cos phi. So we have no more vectors. We simply now are dealing with an ordinary integral with scalar quantities, and we're going to try and evaluate that. Okay, so the steps in evaluating it is, once again, leads us to Fourier transforms and complex integrals, but let's just go through them in detail. So the first step is to write sine as a bunch of exponentials, because we know how to integrate exponentials. And when we do that, we take into, and we also want to, in order to write it like a Fourier transform, we want an integral from minus infinity to infinity. Okay. But because k is the norm of the k vector, this initial integral is just with k positive. And the way we go from that to being a Fourier transform in 1D is simply to add a step function in k. In other words, this is positive only if k is positive and 0 otherwise. So these two integrals are exactly equal, and we've also combined the exponents out here. So here we have ik times tc plus r cos phi, and here we have minus ik tc minus r cos phi. Okay, so we now want to try and evaluate this integral, and because it looks so similar to a Fourier transform where we've actually exchanged the roles of k and x, we're going to try and do it. Okay, but before I do that, and simply to make it easier, I want to give you some more properties of the delta function. So the first one, and that will become useful later when we evaluate the Green's function we have, as well as in general if we take derivatives or compute the integrals. The first property of the delta function that I want to deduce is a scaling property, namely, suppose you have a delta function where alpha is some constant times x, then that's equals to the delta function of x over alpha. And the second one is, suppose we have a function g of x that has simple roots at xi. In other words, g of xi is equals to 0. And then we want to look at what the delta function of g of x actually does. And as you can imagine, it simply picks out the points where g of x is 0 and evaluates whatever function you're multiplying with there. But in order, because you now have g in the interior, you have to take into account that g's scale might be different at different roots. And the way you do that is simply to say that your delta function evaluated at gx is simply the delta function evaluated at the roots, scaled appropriately with a derivative of g of xi. Okay, and you're going to derive this thing in the problem set. A simple approach is to say near every root, simply expand g as a Fourier series, and you'll see that the scaling coefficient that comes in there is just the derivative of g evaluated at xi. Okay, the second thing that I should comment on, where I didn't completely tell you the full story in the previous lecture, is the Fourier transform of the derivative of your step function. Okay, so note that the Fourier transform of the derivative of the step function is a delta function, and we showed that that's just 2 pi, but we then use that fact to work out the Fourier transform of the step function itself, using the identity that the Fourier transform of the function's derivative is just ik times the Fourier transform of the function itself. Okay, so we derived this relation, and what I did in the previous lecture is fine, said therefore our Fourier transform of h of k is just 1 over ik, which is true except if k is equals to 0. Okay, so I just want to give you the complete, and there it didn't matter that I just made that quickie, but here it does. Okay, so in general it does. So I just wanted to fix that and tell you what the full Fourier transform is of your step function. Okay, so here we have, if k is non-zero, this is entirely valid. However, if k is equals to 0, then you have the strange combination where you have a 0 multiplied by some function is equals to a non-zero constant, and that's only possible if the function becomes infinite. So the full Fourier transform of your Heaviside step function, which you'll also look at one of the problem sets, is actually given by h of k is equals to 1 over 2 pi times 1 over ik, which is what we had the last time, plus the delta function of k over 2. Okay, so the Fourier transform of your Heaviside step function is not a function, it is a distribution. but it's a simply examined distribution. Okay, so we're now going to use this to actually evaluate this integral. And as you can see, you here, in order to do it easily, you're going to have to switch k and x. So here, this would look like an inverse Fourier transform, but it's not. We're going to just consider it as a Fourier transform. So in other words, the Fourier transform is just 1 over 2 pi h of k times e to the minus kx. Okay, and so the Fourier transform of that should just be equals to 1 over 2 pi ix plus the delta function evaluated at x. Okay, and this x is now equals to minus this expression here. Okay, and in fact we have two of them just with a different x, where the x over here is just tc minus r cos of phi. And so to evaluate that, we simply say the Fourier transform, so is 1 over 2 pi, so that loses one factor of 2 pi there, is equals to the Fourier transform of this first term, so it's a minus, and the delta function of minus doesn't make a difference, but here we have the 1 over I, in this case it's k, but it will be this term, minus, so that term, so 1 over that term times 1 over 2 pi I, where I've moved the 1, 2 out over there. Okay, so that's the integral of this first term, and the second integral is once again the delta function over 2, so we move the 2 out of the x value, if you would call it there. Okay, so that's tc minus r over cos phi plus 1 over 2 pi I times this x value with a minus in front of there. Okay, so that gives us an explicit expression of this integral over the k variable, simply using the fact that we know what the Fourier transform of the Heaviside step function is, and we recast this thing in k space as a Fourier transform itself, and then we can just write it down. And now to evaluate this, you can actually simplify it further, because we're integrating this Fourier transform, or this result, over 0 to 2 pi. Okay, and note that if you, for these last two terms over here, if you choose a new variable, namely you set phi equals to phi prime plus pi, cos changes sign. Okay, and the integration domain, however, is then sort of minus pi to pi, but it is still the same circle, so it's actually equals to the same integration domain over here. And you then have that these two terms are actually exactly the same, and this delta function term will then cancel out this term here, because the change of variable switches the sign, but the domain of integration remains the same, and these two terms add constructively. So okay, that's just writing it out. We change the variables, so the domain of integration remains the same, and as you change the variables, the cos of phi prime changes. Okay, but you can just relabel it there and there, and that actually gives you that these two terms cancel, but you're left with these two guys, two of them, and you can then evaluate the integral, and it's simply your I multiplies out that I with a minus, that cancels the minus up there, then you have r cos phi plus tc, and then you have the factor of 2, because you have two of these, this other term adding in as well. Okay, so this is then the integral you have to evaluate to get to G2, and we're simply going to write it as some constant that multiplies this integral, and just writing it out in detail where your integral is I2. And so the next couple of steps are going to be to evaluate this integral. Okay, so to evaluate the integral, let's just rename the variables. We say tc over r is equals to minus a, so that a is a positive constant. And we can then express I2 as this, from 0 to pi, 1 over cos of phi minus a d phi. And to evaluate it, we're once again going to use a complex integral. Okay. And we're going to observe the fact that this integral is actually non-singular if a is greater than 1. So that's going to be a condition on a, which actually turns out to give a step function into the solution. So we're going to impose this condition a is greater than 1 using a step function. Okay, and then to integrate it, what we're going to do is use a complex integral. So we're going to say let z equals to e to the I phi, and therefore dz is I times e to the I phi. Okay, and then we're going to have that I2 is equals to the complex integral over the circle where z is equals to 1 of d phi, which is just this expression. We have now replaced I phi with, d phi is equals to dz divided by this thing. Okay, and so that's the minus I when we bring it above, and this is just 1 over z. Okay, so that's where that term comes from. I'm going to rewrite cos as e to the I phi over 2, so there's a factor of 2, plus e to the minus I phi over 2, okay, minus a, so putting the 2 above, it will be minus 2a, and here's e to the I phi plus e to the minus I phi. Okay, so this is now the integral I2 expressed in terms of z, and just rewriting and neatening things up a little bit, we get that it looks like this. And note that the thing that I got wrong in the previous lecture is that in order to apply the residue theorem, you have to have this integral go around in a positive sort of definite direction, so counterclockwise. And we'll do that and then examine the residues inside the circle. And to examine the residues, you have to work out the zeros of this denominator. So we're going to do that. We can write this integral as the numerator over the product. And in order to make it easy to read off what the actual values of the residue is, you have to write it as simple poles. And we can solve these poles explicitly by simply putting this back and solving this quadratic equation. We get that z plus minus is equals to a plus minus the square root of a squared minus 1. And from here we can see that because we're going to restrict a to be positive, and we can see that z lies within the circle, or z minus lies within the circle, and z plus lies outside. Okay, so here we have z minus is in the disk, z less than or equal to 1, and z plus lies outside. So when we evaluate the value of this integral, we simply have to add up the residues inside the circle. Okay, so using the residue theorem with a proper traversing of counterclockwise, the way we've defined z, we have that sort of of our positively orientated curve, we have that this integral, we can simply rewrite this guy in terms of the simple poles with the function multiplied out front. So it's simply 1 over z minus 1 over z minus z plus. Okay, and only this pole lies within the circle. So that's simply the residue at that pole times 2 pi I, and the residue at that pole is equals to minus 2i z minus z plus, and you can see that z minus z plus is minus the square root of a squared minus 1. Okay, the a's cancel out, and there are 2 of them, so here we have minus, or the minus which cancels out with the 1 above, so you have 2i times 2 pi I over 2, the square root of a squared minus 1, and you get that this integral I2 then has the value minus 2 pi over the square root of a squared minus 1. So it's a nice application of a complex integral to actually work out an integral that by other means is actually quite hard to get. Okay, so that now gives us our Green's function, which is actually beautifully simple. it is simply that constant we defined previously multiplied by the step function, which is a condition that this integral is non-singular, in other words, that a is greater than 1, okay, and multiplied by the integral itself, which is just a squared minus 1. And then this r comes from the constant factor that we had in front. So, and if we then substitute back in our definition of a, then we simply get that a square, or a is equals to tc over r minus, okay, and we have that a minus 1 being positive is simply equals to this condition, because t is actually t prime minus t. Okay, so here I've actually, because the Heaviside step function, you can actually rescale the integrand without changing the step function, because all that it cares about is where the integrand changes sign. I simply multiplied everything by r to get the step function in a nice way. And then here below the line, it's the square root of a squared. So here we have t prime minus t c over r squared minus 1, and we multiply it through by r. Okay, so the Green's function for the infinite domain is then just, I've used the definition of r and t, and just written it out in full, because sometimes it's useful. Okay, and over here I've multiplied this r into the square root as well as the c into the square root, and that's what we get. Okay, the other Green's function, or the function that we're going to use when we actually evaluate u, and I'm actually going to do that in steps, because it's quite hard to go from this Green's function that is defined, or sorry, non-trivial to go from this Green's function defined in terms of the norm of the difference between the two vectors, to the actual evaluating the integral. I'm simply going to do it in full, and in order to evaluate the integral, you need the derivative of the Green's function with respect to our source time, and to do that you simply differentiate this thing directly. So the derivative of h is equals to a delta of the Heaviside step function is equals to a delta function with a minus in front, so that the minuses cancel and you're left with this delta function. And then you have to take the derivative with respect to t prime of this square root, which simply gives you minus a half times the square root of the 3 over 2 multiplied by 2 times t minus t prime times minus. Okay, so that's just this expression. The only problem is that this term over here appears to be strongly divergent at the point at which this, at one of the boundaries, in other words, at the point at which the step function's argument goes to 0. You can see then diverges like the square root to the 3. And if you put that under an integral, it's bad. Whereas if you have the integral of the square of 1 over the square root of something that goes to 0 at the boundary, then you can still do the integral, and I'll show you how. But this thing is a very, very difficult term. So what we're going to do is try and get rid of it. And the way we get rid of it is simply to write it as a derivative with respect to r, and then use integration by parts. So to see how that works, so let's work out the derivative of the Green's function 2 with respect to r, and because t prime and r also appear in the same kind of way in both of the Green's functions, we also get a delta function. Okay, but if we take the derivative with respect to r of this square root underneath here, we also get this term, we get additional factors inside. And so what we have here is basically the same type of divergent term with a step function above. And what we're going to do is we're going to simply eliminate this divergent term by substituting in its definition using the derivative of g2 with respect to r. So the approach here is simply solve replace this, use this term to, or use this lower equation to define what h over the t minus t prime squared minus r squared over c squared to the 3 over 2 is, and then we substitute that back into this above expression. And when we do that, we can then express the derivative of the Green's function with respect to t prime is the delta function that multiplies a term over here plus t minus t prime c squared over r times the derivative of the Green's function with respect to r over here. So we haven't gotten rid of this term, we've just gotten it into a different derivative, which will be, as we'll see, it will be easier to manipulate when we actually write out the integrals. And another thing that we actually got it as a bonus over here is that this factor in above here can actually be used to cancel out the divergent term below when we actually take the delta function over here. So this is a much better defined term than what we had up here, simply because we've written it in this way. Okay, so now we're going to actually try and evaluate, or at least simplify the integral from the formal expression we have to a specific set of integrals in 2 dimensions. Okay, and then to do that, I just sort of wanted to draw a little sketch of what the integration is going to look like. It's simply, here's our field point, vector r, where we want to evaluate the function. Here is the source point, the vector pointing to a specific source position, r prime. And this big R, whose norm has been entering into the Green's function, or enters into the Green's function, is simply the difference between R and R prime. Okay, and furthermore, we're going to define the angle, and often that we're going to integrate over is simply the angle between R and R prime. Between big R and our field point R. Okay, so let us now re-express this general integral for the specific case that we're considering. Okay, so we have to integrate over omega, which is the full R2 plane. Okay, except that at least in this case, where we just have g in that case, we limit that integral using this Green's function over here. In other words, R has to be less than, or the radius that you integrate over has to be less than ct minus t prime. Okay, so we're going to, in order to do this integral, we're going to center the coordinate system at the field point where we're going to evaluate it. We're also going to say the direction of R sort of indicates the x direction of our coordinate system, and therefore our angle theta is equal to 0. So when R, the big R, that's the symmetric vector, is parallel to our field vector, then theta is equals to 0. Okay, we're also going to then use the fact that R dot R is equals to R big R cos of theta. Okay, and then furthermore, just to write out, we're going to have to evaluate all our functions, in other words, this g, and the initial conditions at the source point, so r prime. Okay, and the way we're going to then express r prime is simply the difference between the field point, where we want to know the actual function, plus the point at which we're evaluating when we integrate using the Green's function. Okay, so if we then do that, our expression becomes, for our 2-dimensional plane, you can express it like this. You simply have the Green's function, which is symmetrical and depends only on the magnitude of r minus r prime. And we're going to integrate over r, so you basically have the area element of r dr d theta. And then you're going to integrate this source term as at r prime, which is then just r plus r over c squared. And you're going to do a similar thing here for the initial condition. Okay, so here's our initial condition that's given. Here's our initial time derivative that's also given. And here are the Green's functions evaluated at the source point, or source time is equals to 0. Okay, so now I'm going to look at each term in particular. And ironically, the hardest term is actually the term that makes use of the initial condition that's given, because you have to use this G2T prime derivative, which I've simplified somewhat, but it is still got this rather complicated term where you take the derivative with respect to R. Okay, and I'm going to show you how we deal with that. So just to reiterate what we had on the first slide, we're going to break it up into 3 terms. The first term is the term that deals with the forcing. The second term is the term that deals with the initial condition. And the third term is the term that adds the contribution of the derivative of the initial condition. Okay. And the fact, and then just to reiterate something I've previously said, this factor of H basically restricts the domain of integration. So it restricts this G2 to a cone in space-time. And I'm going to plot it for you now that you can actually see what it looks like. And what this immediately means that at least for U1 and U3, this integral of no longer goes to infinity, but it just goes to the boundary of the cone for that given time. Okay, so it gives you an upper limit for R, okay, on U1 and U3, and that upper limit, then instead of going to infinity, for U1, you go to C of t minus t prime over there, and for U2, this upper bound in R then becomes CT. Sorry, U3, this upper bound in R comes CT. We're going to wait a bit with this one because we're going to actually do some integration by parts and you don't need it. Okay, now what we're going to do is evaluate U2 first because it's the hardest one. And to do that, I'm simply going to write out all the details. The first thing I'm going to need is a unit vector that points in the R direction. So it's basically R, the R vector divided by its norm. Okay. And so I can express R prime as R, the field point, plus R times S hat. Okay. And I'm also going to say, let this the original field point make an angle theta 0 with the x-axis of the frame in which we're going to be describing our field point, in the frame in which we're going to describe our solution. And then I'm going to actually be able to give an explicit parameterization for S hat, and that's just going to be cos of theta plus theta 0, I plus sine of theta plus theta 0 in the j direction. And just to give you an indication, this is what we have. We have our spatial vector R of the field point going to the center of the coordinate system that we're going to use. The theta 0 is this angle over here. The theta is the angle between R and big R, so it's that angle over there. And so the unit vector that points in the R direction is simply cos of theta plus theta 0 in the I plus sine of theta plus theta 0 over there in the y direction. Okay, so R is the unit vector pointing in that direction. And when we do that, we can go on and we can express U2 as follows. It's simply now the integral from 0 to infinity dr, because I haven't yet restricted the domain because I've still got this derivative in here that I want to get rid of, times u of r prime evaluated at the source point, where we're going to express r prime as this thing. For the purpose of the integral, this r is basically considered a constant, and then you've split the roles. You basically have the magnitude of the vector multiplied by something that is just dependent on cos. Okay, so you then have this integral of u of r prime 0 over d phi and then dr. Okay, and you then also have this delta function, which is equals to the delta function of r of t minus r over rc times t minus r over c times 2 pi c, the square root of t squared r squared over c squared. Note that this r term over here is actually cancelled out in both the delta function and g2 of r over here. So if you go back and actually look at the expression of gt, you'll see that there's an r term, g2 with respect to t prime, there's an r term in the denominator, and that's actually cancelled out to give you this result, which is very useful because you don't want things going to zero in the denominator at all. Okay, so now I'm going to look at each of these terms and look at their contribution. The first term over here is just a delta function term. So let's look at that. And the way to write that one out is simply, I've just expanded this thing below here in terms of basically t minus r over c multiplied by t plus r over c. I've taken 2 pi out and divided by d theta, divided d theta by 2 pi. And the reason for doing that is this integral is actually an angular average. The other thing I've done is I've moved this delta function that's dependent only on r out from the integral of d theta. So you can actually work out this angular average and then try and evaluate this integral. However, it turns out you don't have to evaluate the angular average at all because this integral is actually zero. And the way you see that is that the delta function over here limits the integral to basically r is equals to ct. Okay. Just note the other thing that I've done in going from this integral to that integral is I've used that rescaling value. In other words, the delta function of something minus r over c is equals to c times the delta function of that something multiplied with c. Okay, and the reason I did that is that when you're evaluating a delta function and the integral is over r, you always want r to be alone there. In other words, you want the function of, say, r minus some other thing. In other words, you don't want ideally don't want a function of r in here, you just want r on its own because it makes it easier to evaluate. Anyway, so that's why I used that rescaling property to rescale the argument of this integral to give this. But this delta function basically fixes r is equal to ct. And the moment you fix the r is equal to ct, these two factors go to zero. The fortunate thing is that this thing can then basically be written as the square root of t minus r over c over the square root of t plus r over c. So the factors of, I've cancelled this divergent factor below the line with a numerator. And so when our delta function fixes r is equal to ct, this term over here effectively becomes 0 over, effectively becomes 0 because the numerator becomes 0. Okay, and I'm just going to write it out since basically delta function is false that. And then you have this thing basically becoming 0 over 2t. Okay, so this red term, despite all the fanciness, is exactly 0. And this is counter to what we expected from the one-dimensional case. Because remember, in the one-dimensional case, when we were evaluating the contribution of the initial condition, we also got a delta function, except that that delta function then basically made that we had the function being evaluated at the sort of the furthest 2 points of our one-dimensional cone, and that made a contribution to the integral. And in this case here, the delta function actually, because of this integrand going to 0, actually gives no contribution. So the full contribution to this integral of u2 is simply this expression over here, okay, which we're going to evaluate next. Okay, so now u2 is equals to t times the integral from 0 to infinity dr, and it's still the infinite domain because I haven't yet imposed the boundaries. And the reason I haven't imposed the boundaries is because I want to integrate by parts, and then it's simply easier to work with the whole domain. Plus this angular integral, and the angular integral is actually only applicable to taking the angular average of this initial condition u at the source point. Okay, so I've moved this Green's function out, and what I'm now going to do is integrate by parts. Okay, and here I actually give the Green's function just for later purposes. I'm going to integrate by parts, and what I do then is simply I say this term is equals to ddr times the full term over here minus what I need to correct it. Okay, and minus what I need to correct it is basically ddr times that term, but because the boundaries are constant and not dependent of r, I can move ddr inside. Okay, plus g2, which is now I can now, because there's no longer a derivative of it, just make use of the fact that there's a delta function, a step function which limits this integration. But what is also true is I no longer have a stronger convergent denominator when I have just G2. Okay, so now let's look at each of these individual terms and try and evaluate it. The first one is, this is a full derivative, so we only need to evaluate this thing at the two boundaries. Okay, so here we go. We need to evaluate it at the two boundaries at r equals to 0 and r goes to infinity. And here I've actually, and in the second term, I've actually given the full, basically substituted in the definition of G2. So to see how that works, the step function basically limits the domain of integration to the cone. So r only goes to ct. Okay, so that gets rid of the step function. The minus c I've put in front here, so it's minus t minus minus c, so we have the ct. The 2 pi has gone underneath this d phi over here, so that it's sort of an average, an angular average. And the square root thing I've left out here, okay, which is a potentially nasty term. We'll look at it again. So let's first look at this first term. So recall that, and this is why I actually left the domain as infinite, for r greater than ct, g is equals to 0. In other words, it's only the cone where g2 is non-zero. So clearly when r goes to infinity over here, our g2 is equals to 0. So that term doesn't contribute at all. Where r equals to 0, you can then, you're basically evaluating u, not at the source point, but at the field point. Okay, so you can take u and it remains constant because you're no longer changing. So it's simply, you can take u out of this integral, and you're left with this integral from 0 to 2 pi d phi multiplied by g2. But g2 at r equals to 0 is also quite easy to get at, because you have r equals to 0 over there, so the square root is just tc of that. R is equals to 0, so the step function is equals to 1, and the c cancels out above and below. So if you actually evaluate g at r equals to 0, you get that it's just equals to minus 1 over 2 pi t. And so then, and as I said earlier, this integral, because u is effectively a constant, u at the center of that domain of integration is simply u of r0 times 2 pi multiplied by g, so the 2 pi's cancel out. This t cancels out over there, and what is left is over here, it's a minus because of this lower part of the integral, so the minus also cancels out, and you're left that this whole term is basically equals to u of r0. Okay, so that first term becomes very, very easy. It simply becomes the value of u at the field point where you want to evaluate it, but just at time 0. The second term I'm also now going to look at, and I've just rewritten it. In fact, I've changed nothing from this point to over there. Is basically this thing. It's evaluated over the whole domain from 0 to CT. Okay, but it's now a gradient, sort of an angular average of the gradient times this other strange factor, multiplied by CT, which is its radius. So this becomes a very, very rough approximation or expansion in an average sense of what U2 would be at, or what the function would be at the initial function at the boundary. Okay. But the average sense is a bit weird because you have this divergent term over here. So what I'm going to do, and it's worrisome, and it's also worrisome when you actually try and evaluate the thing numerically, is what I'm going to do is show you how to get rid of it. Okay. And the way you do get rid of it is you make a coordinate transformation in R. Okay. So we're going to change variables in R. And the way we're going to change variables is simply let R equals to TC sine of P. Okay, so in order, when you do a change of variables, this change of variables has to be valid over the whole domain of integration. So you can only do this if this domain of integration is limited to TC. And let's see what the consequences is of this domain of integration. So it's necessary, in fact, to use the step function to limit your domain of integration before you do this change of variables. So we say let R equals TC sine P. Then you have that dr is equals to TC cos of PdP. So then we can now work out what this so-called divergent term looks like. Okay, so we want to evaluate dr of the square root of TC squared minus r squared. So that's simply dr, which is now this thing, over the square root. And we can replace 1 minus r, we can basically replace the definition of r squared in there, which is basically t squared c squared times, sine squared of p. And what we have then is simply that this is then cos of p. So the cos's cancel, the t's cancel, and it becomes this very simple dp. Okay, so with this change of integration, we've basically changed away this sort of divergent term over here with dp. Okay, and we can then express our integral as u2 is equals to ur 0 multiplied by ct, which is the radius, times by this averaged, in some sense, value of the gradient over that whole circle, or the weighted average over the gradient over the whole circle, multiplied by TP. But when we work out this weighted average, what we basically do is we take this angular average at R prime at a radius equals to TC sine of P. And what that basically means is that we're weighting the values of the gradient at the boundary more heavily in the actual working out of this integral in the terms inside. So basically this thing over here, in some sense, is the averaged radial gradient multiplied by R. So this whole thing is an approximation of the initial condition on the boundary. But the average is worked out with a non-uniform distribution of points that weights the importance of the gradient near the boundary as being higher. Okay, so I've just written that. And so in some sense, this expression becomes similar to the influence of the initial condition that we derived in the one-dimensional case in an average sense. Okay, the only thing to notice is in the one-dimensional case, you had the possibility where you had an initial wave and it just was like vectored through and the amplitude remained unchanged. When you do this in 2 dimensions, the same thing doesn't happen. You don't start with one bump and the bump remains the same. What you do instead is that it tends to dissipate. And the reason it tends to dissipate, suppose that you had a positive initial condition, in other words, a hump. Okay, and by I mean compact support is that the hump goes to 0 as R goes to infinity. Okay, what happens then is that because you have a hump that eventually goes to 0, at some point this gradient, which is basically the radial derivative, will become negative for a large enough R. So at some point this thing actually detracts and it actually decreases the value of the function. So unlike the one-dimensional case where you had this sort of fixed shape that was maintained and the amplitude over time remained roughly constant, in two-dimension the amplitude tends to decay away. And this is something you see if you look at waves on a sheet. You make the initial amplitude in the middle and then it sort of runs away in rings. And you'll see this when we actually try and evaluate this, or when you try and evaluate this integral in a problem set as well. Okay, so this is just one of the properties. But the other thing to notice is that it's very easy to see from the solution at times t equals 0 that you just have that u2 is your initial condition as well. Okay, so let's now, for completeness, and this is the last slide, work out the expression for the other two terms in the same coordinates because it just makes it easier to evaluate. You once again to have your Green's function over here where that step function limits the domain of integration to a cone, and because there are no derivatives you can simply implement that straight away. Okay, so for the integral that requires the forcing term, it's just from 0 to t prime minus t over c times r dr over c squared. Okay, times our Green function, and I've moved the Green's function out of the angular integral because it's not dependent on the angle, just rather the norm, the amplitude of the difference between the two vectors. And u3, here I've made explicit the domain of integration just goes to ct, and you have the same thing. Okay, so once again, because this domain of integration is already limited, I'm going to set let r, reparameterized r with sine p, and I'm going to express our r prime vector is equals to r plus t minus t prime c. And then r0, which is just going to be this r vector when t prime is equals to 0, is just going to be that. Okay, so once again, that sketches it. The step function h is only non-zero in this cone, the cone of dependence of p of r and t. And we've now just parameterized r within this cone in this manner. Okay, and if you do that, you can just go step through the whole process. You can write down your Green's function over here, so that's just g2, and you've already posed this part of the step function over here, so that's the first term, that's h. The 2 pi has gone over here to make it obvious that we're taking an angular average. The square root is given here. You have c that cancels out with a c squared, and you're left with 1 over c over here. You have this r that comes from the Jacobian also in here. Okay, just with a u2 case, the r cancelled the actual derivative of the Green's function. Here it's retained. Okay, and then you can actually change it to the same set of coordinates to try and get rid of the singularity over here below. And then once again, what you do is simply make use of this coordinate transformation. The way we do that is simply, here as r is just c, r over c. Okay, so you lose the c, is just t minus t prime sine of p. Our dr is just t minus t prime c cos of p dp. Okay, and then the square root is just the same trick that we did for the u2 case. It's simply this factor squared minus r squared, which is then expressed in that way, which is then just a cos. Okay, so you simplify it and you have a t minus t prime cancelling out at least one of these. C cancelling out that C, and what you're left with above is t minus t prime sine of p, and the cos p is cancelled out, that cos p over there, dp dt prime. And that's an integral you can evaluate quite easily. It's simply take your forcing term, evaluate it at this vector r prime, depending on your t prime, okay, for a fixed p, okay, evaluate it, multiply that then by sine p times t minus t prime, and then basically do this integral. Right, so this is an entirely easy thing to program or to compute. You simply can use sort of sum up all the contributions of this averaged integral. Another thing, let us now look at the other term that depends just on the initial condition. This is the term that comes from if you've specified the derivative of u with respect to t at t0. That is simply equals to gt times g, okay, g2. And what you have there is, once again, this g2, you have the same factor over here in both integrals, okay? So you have a t, which I've taken out in front, sine p dp coming in, okay? You're evaluating the integral at t prime is equals to 0, so you're using this r0 integral. In other words, you're simply going over this yellow domain over here, okay? And then you simply, once again, do a weighted average of the u with respect to t. But unlike the case where you were looking at the initial condition, not the time derivative, you are evaluating the thing much more uniformly in this whole domain. So you actually have u of t over the whole domain contributing it, just as we actually had in the one-dimensional case. Okay, so this is what the sine p factor does, is simply make sure that the evaluation is uniform, because you are evaluating r0 at tc sine p. So this fine factor then basically makes it a uniform average that you're taking. And then you're multiplying it again with t, sort of to get the dimensionality right. Right, just to prove, in fact, that the solution does limit to the right thing, in other words, that u3 at times t equals to 0 just becomes ut that's given. Let's evaluate it. So u3 at t is equals to 0, okay, is can be evaluated in the following way. At t is equals to 0, u of t is just evaluated at r. Okay, so it's ut at r, and then the integral, and that's a constant. The integral goes from, we want to evaluate du3 dt. Okay, so the first, if you take the derivative, you lose this t, okay, plus this term that you then evaluate at t is equals to 0, plus t times derivative of this thing with respect to t, but that's always 0 at t is equals to 0. So you don't have to worry about that term. So you're just left with this term. So you basically have ut at r, which is the field point, multiplied by this integral over here. The integral from 0 to 2 pi d phi over 2 pi is just 1, which leaves us to evaluate this integral. Okay, and that's just equals to minus cos of p evaluated the boundaries, which is equals to 1. So then we have that u3 of t at t equals to 0 is just equals to u of t at r and 0. Okay, so that just proves that the solution we've written down in terms of these integrals actually behaves as what we expected. And actually gives us the correct initial conditions back in the limit of t is equals to 0. Okay, so this concludes looking at the Green's function for 2 dimensions. It's been a bit of a long lecture, but it is useful to do at least once, because this type of theory is used a lot. And next time when we go and look at 3 dimensions, which basically has formed the foundation of all our electronic industry and how radio waves propagate and how radar is done, it's useful to actually have a feel of how to evaluate these integrals. They're not easy, but it's worthwhile to go through and actually look at how the integrals are evaluated and the interplay between the vectors that enter into them and the way you actually, when you integrate it, use the scalars or the scalar variables to actually do the evaluation. Okay, so that concludes today's lecture. Thank you very much.